and thank you for doing this.
All right, thank you for that wonderful introduction. As mentioned, I'm Chris. I'm a PhD candidate at Clemson University, and today I'll be helping you guys learn how to ask the right questions with machine learning. So, first we're going to start off with a quick poll. I want to know how long do you spend choosing a method to solve a problem? You know, there's always this phase before you start actually doing all the implementation for something. You have to figure out what you're doing. So just there's a couple of options down there. So let us know what you think on that. All right. So today I'll be going over a couple of things. Mostly the focus of this, as mentioned, is on asking the right questions. But to get there, I'll be giving a brief example on why you need to ask the right questions, and then go over how I've done this in my own research. So I'll give you a brief introduction to what topic models are, and go over the quest that brought us to developing a model called cluster latent Dirichlet allocation to solve one of these problems. And then after going over this case study, I will go over some general advice on how you can apply this to broader problems. All right, so let's get started. So, for a nice little example problem here, suppose that you've got a text reading application. You've got a client who wants you to create something that read text to the vision impaired. So they've got a camera sort of set up, and they need to take those still images and convert them just to raw text data. And certainly, I mean, accuracy is important for this. If they're, especially if they're reading like a legal document or something, you want to make sure that everything is just right. And the client agrees. So they ask you to create the most accurate system you can. So let's come up with what is the most accurate system that takes images and converts them to text. So this is the most accurate thing that I can think of. You take the image and you email it to about 100 grad students, offer them some Starbucks gift cards if they transcribe the text for you, and once you get enough responses that all agree with each other, then send that back. And if it takes longer than some specified amount of time, just keep sending it to more people. This should basically give you perfect accuracies, and thus, it satisfies your accuracy constraint. Perfect solution, right? Of course, this is ridiculous. This scores well on your metric, but it doesn't actually solve the problem. For one, there's sort of this implied constraint of being reasonably real time. And I don't know if you've ever emailed grad students, but as a grad student, I can tell you that we do not respond to email promptly enough for this to work. This is also probably prohibitively expensive if you're handing lots and lots of these gift cards out. So the problem is that the question was basically the wrong question. Instead of looking for the most accurate thing, you need something that is accurate enough within the time constraints. There's a lot of other information that wasn't captured by the metric. So of course this is an exaggerated example, but this danger is all over the place. And so it's important to make sure you know what you actually need. So now I'll tell you about my own falling into this pitfall. But first I need to go over the basics of what topic models are. And so these are a sort of generative model for doing text analysis. Basically, you assume that you've got a couple of distributions. You sample from a topic, you sample from the topic mixture for a document, and you just keep doing this until you generate your documents. The exact specifics of this, if you want to look up latent Dirichlet allocation, there are some great papers on how this works. But the basic idea is that you have to infer these topics that are part of the model rather than part of what you see. So there's a couple ways to do this, but basically you're iterating over documents, and it's a lot of trying to just modify things into something that looks kind of right. So the specific one that we were interested in is dynamic topic models, and this is relaxing one of the constraints of LDA that we're looking at data that changes over time. And so each of your documents, instead of being all considered to be generated at the same time, are separated into discrete time segments. And each of these has a distinct version of each of the topics that you're looking at. And so what we get out of this is we get an evolution of these topics over time, so we can see how the language changes, we can see how the proportions change, to see if if somebody gets if physics becomes more important within a overall science journal or something. And so there's some very useful outputs of this. However, because of the time dependencies and the way that they're arranged, there are a lot of complications to actually inferring this model. So we wanted to apply this to a fairly large data set, and our obvious approach was just parallelize it. But of course, there's a lot of data dependency and very interconnected things between the parts of the model. And the original code was also not designed for performance. So this turned out to be quite a bit more difficult than we thought. And after I had been plugging away at this for about 4 months, we asked a very simple question. Do we actually need this? And we took a step back and we asked, what do we actually need from this? We need something fast so we can actually run it on the size of data that we have. So presumably that means parallel code, but we need something fast. We need something that can extract topics from different time steps so we can preserve that information. We express information about the way that those topics change, both in their form, what words are used, and also how important they are. And certainly a parallel dynamic topic model code would do that, but we found another way to do this. So we decided to, instead of trying to keep all of the topics linked while we're doing all of this inference, we do it all with local information and then link them afterwards. This lets us take advantage of a lot of parallelism and really simplifies the computation so we can actually run this quite quickly. So we came up with cluster latent dirichlet allocation, where we run latent dirichlet allocation independently on each of our time steps of data. And then we cluster these resulting topics, and each of these clusters basically works the same way that the dynamic topics in a dynamic topic model do. You have members from different time steps, you've got all sorts of sort of local things to look at, but also this global picture that you can use to determine how topics are evolving. And so if you're interested in learning more about this, I do have a paper on arXiv about this that has been in development, and there's a link provided. We did pretty well at doing this. We got 2 orders of magnitude faster than the original DTM code. We actually get more detailed topic evolution information than DTM does, and have a couple of other different properties. So this is not an approximation. This is something else that solves our problem. If you're interested in the implementation also, we have that available as well. And there is an active project to construct this using ECL, because all of the building blocks of this are there. So we're working on that. Hopefully we'll get that out to you guys soonish. The important thing to take away from here is that we tried something that was way harder than it needed to be, realized we didn't need to do it, and then we're able to find a much simpler solution that did solve our problem, even though it is a very different kind of solution, but it solves the problem, and that's what matters. So sort of to take this back to a broader perspective, rather than starting with the tool that you want to use, because you happen to like that tool or you've used it before, it might not be the right tool for what you need. So start with, instead, what is the problem that you want to solve? What do you actually need? What is the big picture? What's the final application? What are you trying to do with this? In our case, we were trying to find out, how the access to supercomputing resources changed what people researched. There's a lot of tools that could do that for us. So we also need to look at what does your solution have to look like? What kinds of input do you actually have? And what does your output need to contain? And also to look at, what are the constraints are there? Because while certainly the solution in my original example with the text reading, it has the right kinds of input and output, there's that really important speed constraint that wasn't addressed. And then you also need to figure out how do you evaluate success, because what you can measure easily and what you actually need to measure may be very different. And this is a trap that a lot of people get into. I'm actually writing a paper right now about this trap. So fingers crossed you'll see that sometime this year. It's important to evaluate things in the context of the problem being solved. What is your application evaluated on? How do you distinguish a good solution from a bad one? And how can you measure that difference? Because ideally you would be able to not just know it's like that's a good solution, that's a bad solution, but have sort of a range between there. And so after you've thought about these, you can finally actually start to solidify what method you're picking. You can look at these requirements and figure out what methods are even possible for this. What takes the right kind of input and produces the right kind of output, and narrow this down based on the constraints that you have. And then once you've narrowed this down to things that will solve your problem, you can figure out which one will solve it best. You can look at the trade-offs that these methods have and what your priorities are for your application, and then start to actually select the right things. All right. So we've got another poll, and this is just to sort of find out what you took away from this. So please answer if you previously thought a lot about what methods you used before you got into actually implementing them, and if you will in the future. All right.
All right. Thank you, Chris. We're going to take a second while you look at the questions. It looks like we've had some really good ones come in. And we're going to look at your first poll. The question was, how long do you spend on choosing a method to solve a problem? So 4% of you just take the first one that fits your needs, which I guess that's fine. 33% of you search for a few common methods or related tasks. 54% spend some time evaluating methods, and 8% do an exhaustive search before selecting the best choice. So those are really interesting answers. All right. All right, so our questions. Here's the first one. How much domain expertise do you need to apply these methods for topic classification?
So certainly, if you know nothing about the domain that you're working with, if you're analyzing a bunch of chemistry data and you are not a chemist, you're going to have some problems. When we were doing something like that, we had a couple of domain experts that we would call in after we had run these topic models and ask, do these topics make sense? But as far as actually running the models, most of the models based on latent Dirichlet allocation that have code for them are reasonably straightforward to use. There's some management that you'll need to do to make sure that your data is in sort of the right format. But you don't need to be like a machine learning expert to get things out of these models. Although certainly it's handy to have people around to make sure you don't fall into traps and whatnot. So I think that they're sort of moderately accessible. And I am hoping to provide some more information on how to make them more accessible to make sure that that everybody actually knows what to look out for.
All right. Yeah. All right. So it looks like our second question is, how do you determine the right number of topics to configure the parameters a priori for topic modeling algorithms? Sorry,
so
that's a
this
long,
is actually
one.
Yeah. This is actually a very interesting question, and this is what got me onto this particular set of questions. So there's a couple of rules of thumb about this, such as to run like 20. I see a lot. Some people run for like 100 or 1,000 and then cut to the top 20. But the problem is that there's not really a very well-established way to determine what the right answer to that is. And there's a couple of metrics that people have been using to determine this. But there are problems with those metrics. So I'm actually writing a paper about this right now because this is a much harder question than it sounds like. So stay tuned for that. But honestly, I mean, the right answer is going to come from looking at what you need from it. So if your application is about trying to sort documents into various kinds of buckets, then you need to have the right number of buckets for that. Whereas if you're just trying to explore a corpus and find out what's there, then you may have a different answer for that.
All right, wonderful. All right, perhaps when you finish that paper, Chris, you might be open to doing a guest blog on our blog. I think we'd love to, have some information on that. Yeah, awesome. All right, so here's the next question. What type of intervals are appropriate to segment documents in time steps? Is a day fine or a month? Are there good rules of thumb?
So this is also an interesting question, and this is one of the reasons that we're starting the process to put this into ECL so that we can actually run experiments on this. So for our experiments, we did this off of a year because the data set that we had this left us with a fairly substantial body of data per year, but then still let us see how things were organized. But the data that we were working with was abstracts from conference submissions, and conferences are sort of scattered all throughout the year, so it doesn't make too much sense for us to break things up by month. But for other applications, a day or a month might actually be the right answer. So again, it comes back to looking at the application that you have, thinking about what you're looking for, what you need from it, and then also making sure that that doesn't violate one of your constraints, because LDA performs very strangely if you have too little data. So you need to make sure that your bucket size is large enough that you have enough data to work with, but fine-grained enough that you get the information that you need out of the application from it.
All right, wonderful. All right, we're going to give a few moments for some additional questions to come in from our audience, and while we do that, we're going to look at your last poll. So the question was, did you previously think a lot about what methods you used? Will you in the future? And so we have two answers on that. It looks like around 30% are saying, I did not, but now I will. and 68% are saying I did and I still will. So that's good. So we're glad that no one is feeling contrary and that no one refuses to do this. I think it's a good opportunity. All right. So here's another question. Can you tell me a little bit more about CLDA, about how CLDA combines topics across time steps?
So what we do here is actually, it's sort of painfully simple, is that we actually just take all of the topics, throw them into one giant bin, and then run clustering on that. In this context, each of the topics can be looked at as a vector, and so it's really just about as brute force as you can get here. We're just running k-means on this. Future work will also look at doing other ways of clustering this, but what you get out of this is that each of these clusters has a bunch of topics assigned to it, and these are drawn from any of the time steps since we all just throw them into the same bucket first, which means that we can look at the clusters and say, it's like, okay, in this time step, we got a couple of these topics, here that all sort of capture different parts of the same idea. And then here, it wasn't talked about at all. So we can get some information about topics being born or dying off, or even periodic topics that show up, like every 4 years or something. If you're interested in how that works, we have some interesting graphs in the paper that should be attached, the CLDA archive paper. It's definitely, it's quite different from how a lot of other topic modeling approaches go, because it is constructed so differently from the, linking things afterwards rather than during the inference.
All right, thank you very much. So that is all the time that we have for our questions today. So if you've submitted a question and we haven't been able to get to it, we will try and reach out to you individually with an answer, and we will try and include those in our follow-up blog. All right.